Hello everyone, and thanks for joining me today. My name is Richard Barry. I am a Senior Principal Engineer with AWS IoT, although I specialize on the device side software rather than the cloud side software. I'm also known as the original author and promoter of the FreeRTOS project. Today we're going to look at some of the options AWS IoT provide for edge software, look at the functionality which comes with those options. And then we're going to dive a bit deeper into the libraries that come with the latest FreeRTOS versions. We're also going to look at some of the work we've done to make sure that those libraries are applicable not just to the FreeRTOS community, but the whole embedded community. And that we'll look at a little bit of source code to show you different use cases for those libraries. And then we'll summarize at the end with looking a little bit beyond just the development and other ways that AWS IoT help you scale beyond development into production. Okay, so the things in the Internet of Things are devices. These are physical devices which sit in the environment. Typically, they interact with their environment and they are going to send data to the cloud. On this diagram at the moment, the devices sit in the yellow hexagon there on the left-hand side, and they are going to communicate through that little cloud logo with a door in it. That represents the gateway for the data to get into the cloud to the cloud services on the right. Now, this diagram does nicely call out some of the things like, the encryption, connectivity, fleet management, auditing, all of that functionality it's not differentiating functionality. It just has to be there in order for you to develop and actual value for after you've got your data into the cloud. That enables you to, of course, concentrate most of your work, your engineering work, on adding the primary business logic rather than that undifferentiating functionality. And the same is true for the device software. Here I'm showing different options we have for device software. And of course, you can write your own software. You can write all of your software and connect to AWS IoT. These integrations provide a lot of that undifferentiating work, so we feel that they will get you there faster. If you have knowledge gaps or anything like that, and then they will be filled by using these different options. So we're starting here with the device SDKs, AWS IoT device SDKs. These range from the embedded C SDK for devices through to other languages like C++ and JavaScript and Python. They all provide similar functionality, or the same functionality in the different languages, and they all provide that undifferentiating functionality for you. Now, in the middle there, we have FreeRTOS. A lot of this talk is going to go into FreeRTOS in more detail, so for now, I'm just going to say FreeRTOS shares a lot of its libraries with the embedded C SDK. Now, FreeRTOS really is designed for microcontrollers. These are the very small processors which are, they surround us every day in our lives. Typically, a FreeRTOS application, although the kernel takes between 10 and 20 kilobytes of code, a FreeRTOS application would run on a device with a few hundred kilobytes of program space. On the right-hand side, we're showing AWS IoT Greengrass. Now, this is for much larger microprocessors, with megabytes of memory. And they're obviously a lot more capable with compute, but in addition to that, Greengrass does a lot more in regards to things like messaging management, data management, synchronization. It enables you to run machine learning inference capabilities at the edge, that kind of thing. Now, there is a whole talk about AWS IoT Greengrass, so I'm not going to go into it much more detail in this talk. If you're interested in running edge compute, by edge compute I mean things outside of the cloud, on larger processors, all those capabilities, I'd really encourage you to go and look at that talk. So for now, I am going to look at FreeRTOS. And remember I said FreeRTOS shares a lot of its libraries with the embedded C SDK for devices. So implicitly, I'm also talking about the embedded C SDK. Now, FreeRTOS has been around for a long time. This diagram here, or this chart here, shows you the growth in the number of downloads over those years. It's downloaded about once every 170 seconds now. These are all actually undercounts because you can obtain FreeRTOS from lots of places. We're only counting the number of people that download it directly from us, and the statistics actually come historically from SourceForge, where it's been hosted. Where you see that orange line turn to the yellow line, that's where we changed to GitHub. And we'll look at GitHub a bit more soon as well. Now, moving to GitHub has been fantastic. AWS's stewardship of FreeRTOS has really enabled us to scale the team and scale the functionality. GitHub has really allowed us to scale that collaboration, not only with the community, but we have 6 or 7 silicon vendors there who are collaborating with us. Okay, so as I just said, FreeRTOS is under the stewardship of AWS now. AWS obviously have an interest in making sure that many devices that run FreeRTOS and connect to AWS can really do so with the least fuss possible, and of course, as securely as possible. So there's a big incentive to make sure that the kernel's kept up to date and that it runs on the latest architectures, for example, and that we provide all these other libraries. There are also less obvious benefits here as well. For example, our tests now contain a growing number of memory safety and thread safety proofs, and they are provided by the automated reasoning group within Amazon. And additionally, it is specifically of interest to IoT, where devices are distributed geographically. FreeRTOS users now benefit from Amazon's worldwide best practices in investigating vulnerability reports, security disclosures, patching software. So you can see Amazon's stewardship as FreeRTOS really adds not just to the functionality, but also to the reassurance you get in using this software. So all that confidence now, I'm really pleased to say that we are adding to. Again, with Amazon's backing, we are able to now provide long-term support as well. What does long-term support provide? Well, it enables you to take a device from its initial design all the way through to production and beyond on a single version, on the LTS version of these libraries. That means that those LTS versions will get critical bug fixes, but all the additional features are developed on the main line and future releases. So you can, if you need those bug fixes, you don't have to bring in the head revision of code or any disruption that would give you in having to retest and that kind of thing. You just get those critical fixes. So you can see we're adding these value propositions all the time. Okay, so now we'll move on to look at some of that additional functionality I just mentioned. This is reInvent, so we are going to focus predominantly on the connectivity and the security. Normally, I talk about the kernel, the scheduler in FreeRTOS. We're going to start with looking at reference integrations, because these provide you everything you need, as I said, to create a secure cloud connection. This diagram here is representing an application, and I've hidden a lot of the complexity in this kind of middleware box in the middle, because what I want to demonstrate here is some of the simplicity, the ease of use that this provides you. That comes from making the most of the multi-threading effectively. What we are doing here is running fairly complex pieces of functionality in agent tasks or daemon tasks. These are tasks that run in the background, yeah. I'm going to actually show some source code a bit later about how we do this with MQTT. So if we think about OTA now, OTA is the over-the-air update where if your device is deployed somewhere and you want to send a new executable image to it or other image to it, maybe you're improving the functionality, unlocking features for somebody, for a customer, or patching it, then our OTA agent is actually integrated into AWS IoT's device management. Now, of course, you can do OTA any way you like, just like you can provide all this software any way you like as well. The OTA agent here, it has to manage all the kind of sequencing, the data management, the state management, the timing, all these different things. And if you had to do that yourself, then that would put some burden on how you actually execute it within your application. If you run it as an agent, you start the agent when your system boots, it gets notified of a new image, it downloads the image. Very importantly, it checks the integrity of the image. Has it been tampered with? Has it come from the correct source? And then just lets you know when the new image is available for you to execute. So you can see how that improves a lot of the usability. Now, if we break out the that middleware box and look at what is inside there, you'll see where some of that complexity comes from, because you've got libraries interfacing with libraries, not just libraries interfacing with the application or the hardware. Okay. So what we've done over the last few weeks and months is really asked ourselves, how can we bring this functionality to the wider community? Because if you look at this, what you'll find is that a lot of the protocols, in fact, everything there is just a standard internet protocol. Okay, there's nothing AWS specific about it, so it's benefit to everybody, not just FreeRTOS users, not just AWS users, but the whole embedded community. The OTA agent I said was AWS specific, and then we also have other clients that give you access to AWS IoT services, like the Shadow client and the Jobs client. And everything else really is just standard internet protocols, okay? So what we have done to bring these libraries to the entire embedded community is to look at them, refactor them, and make them very, very modular, or what we say composable. We've boiled them down to their base functionality, made them as simple as possible, and then we've put them in their own Git repository. So you'll see here all the standard protocols in the FreeRTOS account in GitHub, and the clients that allow you to access AWS IoT services are in the AWS account in GitHub. Why have we done this? Well, I've opened up all the, or the reason we've done it is to open up a very wide range of use cases. So we've already looked at the reference integrations, okay? That's a kind of one level of an integration. At the other end, it covers no integration at all. If you want to bring in a library just by itself, you can now submodule it into your application and have that link back to its its source of truth in GitHub. We're actually going to look at some source code of how you can do that momentarily. Next, the next use case I'm talking about here is just easier distribution for other people. Other people distribute the kernel, and they can do the same with these other libraries, because the kernel is now in its own Git repo as well, as is the TCP/IP stack. Other recent changes to make it easier for people to use them and consume them. The next one we're going to come on to in this row then is the classic FreeRTOS distribution. I call this the classic because this is the way FreeRTOS has been distributed for many years, and it's as a package of libraries with a whole raft of examples that demonstrate how to use them on various different hardware platforms. Now, although we still do that, of course, for FreeRTOS, but now we are submoduling in the libraries rather than it being monolithic, but we're also able to do that in an RTOS agnostic way. So the green boxes here are demonstrating the packages of libraries that you can also obtain. You can see there's one for FreeRTOS and there's one which is RTOS agnostic. And then again, we come along to what I've mentioned already, the reference integrations. If you want a reference integration, then you can go to the AWS IoT device catalog. The URL was on the previous slide, I think. I forgot to mention it there. Or if you go there and you filter on FreeRTOS, you'll find them all. They're all pre-tested, pre-integrated and pre-tested, running on various different hardware platforms with various different network connections. You can also go to the freertos.org site and follow your nose through the menus, and you'll find them there as well. So let's dive a little bit deeper then in how you would use those libraries to demonstrate some of the things I've just said. Because MQTT is what we're going to focus on. This is independent of the operating system. Don't need an operating system at all, in fact, which is what I'm going to demonstrate here. And it's independent of the underlying TCP/IP stack. Right, to demonstrate this, I'm going to say I have a hypothetical application. That's what the top left diagram here is supposed to show. Maybe that's a small processor, 8 or 16-bit processor. It already has connectivity. How does it do that? Well, it has a radio. Very, very typical if you have a Wi-Fi or a cellular modem or radio, then the TLS, which is the encryption protocol, and the TCP/IP stack will be offloaded onto that radio. So we have this already in the field. Now we want to bring in MQTT. This is what I'm demonstrating in the arrows transforming it. We're submoduling in the blue. So we're submoduling in just the core MQTT. So our branding for these libraries is core, because they are just the base simple functionality. And how do we do that? How can we do that in a way which is kind of agnostic of the TCP/IP stack? This is what this is this piece of source code is demonstrating. So if you look at the second line up, you'll see the MQTT API. And the second parameter there is the transport interface. The transport interface is just a structure that you provide. You'll see that being completed in the 3 lines above that. The first is the context. Now that can be anything you like. The MQTT stack doesn't look at that. It just passes it into your send and receive functions. It may be just a TCP socket, maybe a TLS context, maybe it's some kind of context out to an offloaded TCP stack. And then you have to provide function pointers for your send and receive functions. Here I'm showing kind of my TLS send and my TLS receive. You've already got those already. You're sending and receiving already. This is a brownfield, it's what we call a brownfield application. It's an existing application. You will have to provide a wrapper around that, a very thin wrapper around that, just so that the signature of that function matches what the function pointer expects. And we have examples of doing this, of course. Now then, how does that work? And to demonstrate that, we are going to, how does that actual send and receive work? To demonstrate that, we are going to look at how you would publish. Again, the second line up here is the MQTT publish. And we are passing in all the information we need to create that publish message, MQTT being a publish subscribe. Again, it's just a structure. You can see the structure being filled in there in the middle of the screen. And that when we initialized it, we created this context and we passed that context in to that publish message. That publish message is then going to create the publish packet, and it's then going to call your send function and pass in the context. So now you're inside your send function, and you have your context, which may be the TLS context through which you can send. Now then, I said this was a single threaded. Actually, I didn't say that, but I implied, because this is a small application, we're probably not using threading. So how do we then manage the protocol? If you're not using multi-threading, then you are going to have to periodically call this process loop function. Again, it's the second line up there. I should incidentally say all these are very, very simplified. I've put these asserts in there just to represent the fact that you should obviously handle the return codes in some way which is robust for your application. So we've sent our publish, and now we're going to kind of keep the protocol ticking over. We can do that in a couple of ways. The way I'm showing it here is I'll put a timeout in there. So I know I'm waiting for a publish acknowledgement in my particular design. And then I'm going to wait there. I get a call back when it comes in, and I can then carry on with the rest of my application. Alternatively, I just could put a 0 timeout in there, and then I'd have to make sure that I called it more often until the acknowledgement was received. You do have to keep periodically calling it, of course, because there's events happening on the socket and that kind of thing, timeouts that it has to manage.
Okay, now we're going to come on to the more traditional FreeRTOS use case. So we've looked at the reference integrations. So the more traditional use case where we have the multi-threading and a small set of libraries here. So now, again, on top left, I've got our existing application. We've brought in the MQTT. Bottom right here, I'm now also submoduling in. Again, the blue is the submoduling in the kernel. Now, I'm showing the kernel here, but it doesn't, I'm showing FreeRTOS here, but it doesn't have to be FreeRTOS. So how do we then go about using the MQTT library in this multi-threaded application? Now, remember I said we keep the MQTT library as simple as possible, so the multi-threading is not built into the library exactly. It's not built into the source code of the library by itself. We affect multi-threading by creating one of these agents that we talked about before. That means that the agent is the only thing that's allowed to call the MQTT API. Therefore, it's kind of naturally serialized. Now, why do we do it this way? Several different reasons. We want to be able to keep the libraries as simple as possible, like I say, because that helps us with things like making sure that we are compliant with kind of de facto coding standards like the MISRA coding standards. And also, you remember I said we were doing these memory safety proofs. It makes that kind of thing much simpler as well. So this blue box here is demonstrating the structure of the MQTT agent. It's going to wait on a queue. That's the first thing it does. That means we can also make it lower power. We're only going to be executing anything when there's something that needs to be done. If an event comes in, it's going to then process that event. And then at the bottom there, you can see that housekeeping. That's where we call the process loop function. Remember, we have to keep calling the process loop. And then we go and block on the queue again. Now, because we have to keep calling that process loop, we don't want to block indefinitely. So we're going to block for a time period. If we exit without receiving the event, we call that process loop again and go back up to the top. So again, even the agent structure is very simple, and we look at the source code for that as well. Anything else that wants to interact with the MQTT does that through an event queue. So if the socket, which is connected to the MQTT broker, gets an event, maybe that publish acknowledgement has come back, it can send an event. It will cause the MQTT daemon task to unblock. It will process that event. Now, if the application writer wants to send a publish message, they don't call the MQTT API directly, but instead that published data is packaged up, sent in the queue, and then it is interpreted by it's received and interpreted by the agent thread, as is shown here. So this is, again, a massively oversimplified structure of what these agents look like. You can see it's waiting on a queue. It receives a message. I'm only showing the publish here. And it calls the MQTT API in exactly the same way it did before, and then calls process loop at the bottom. Notice now that the process loop has a 0 block time because we want to make sure this is as responsive as possible. Okay, so far we've only considered simple connectivity. So what else do we need for secure connectivity, cloud, secure cloud connectivity? And of course, we want to be able to authenticate. So back to this diagram, here we have TLS, which I kind of skipped over before. TLS is the protocol that we use every time we connect our web browser to an HTTPS server. The web browser needs to make sure that the server is genuine. It does that by obtaining a certificate from the server, and then it needs to check the certificate is genuine, and it does that by checking the signature, so that the signature of the certificate, and that would have been signed by a certificate authority, which is one of the ones listed by your browser as being trustworthy. Now, if a device wants to connect to AWS IoT Core, it's exactly the same. We need to make sure that it's the correct endpoint. AWS IoT Core is the MQTT broker in this case. So we use certificates for that as well. But now we need mutual authentication, okay? So the device has to do the same to authenticate itself to AWS IoT Core. It can't just let anything connect. It has to be authorized to connect. And that brings in the other boxes in this diagram, which we haven't mentioned yet. Now, the certificates and the keys which are used for this authentication have to be stored on the device so they can be, so the certificate can be presented. And the keys which are used for these certificates and the secrets management, ideally we don't want those to be accessible to anybody. We don't want it accessible to the software, and ideally not accessible to somebody who's got access to the device. So you can store these in things like secure elements, secure enclaves, trust zone M on something like an ARM V8M. And that kind of makes sure the keys physically are secured. And then we want to do the same in the software, of course. There's no point having a key which is in secure storage if we're just going to read it out of RAM to use it. So we don't have to read it out of RAM. We use another widely used API, I mean your laptop will use this, called PKCS11. Now, that enables us to access keys using session-based handles without actually having to look at the key. PKCS is a large API, okay? On here, I'm just mapping some of our functionality to that PKCS11 functionality so you can see that we're only using a subset of it. And again, we have this kind of core PKCS as well. So now, what have I done? I've brought the connectivity in. It's my application, I have signed a certificate, and I've provisioned my device. So getting the credentials, the keys and certificates onto the device is provisioning. That was okay because it's on my desk and I'm doing it one-to-one. Now, maybe I am interested in AWS IoT because I know that it can handle millions and millions of my devices at once, and I expect my product to be very successful. So here you can start to see the practical challenge. how do I, when I was just one on my desk, I could do this process myself of provisioning, signing and provisioning. Okay, now I want millions and millions. How do I do that? And it won't be a surprise to you to learn that AWS provide help here as well. So not just help designing your product or connecting, but also how you do this at manufacture time. How do you go to market much more easily? Now, don't worry too much about trying to follow the detail in this little flow chart. This is just trying to show that there are different options for you here. You have to make certain choices as you go to market. Things like, do you want to provision the device? Do you want to get the keys and certificates onto the device when you manufacture the part or when you turn the part on? The cloud side of the provisioning, the registration of that part with IoT Core, do you want to do that when the device turns on, or do you want to do it up front? So you've got lots of different options here. I'm going to take the simplest path here. I'm just going to go across the top. I'm going to say that I want the keys and certificates on my device at manufacture time. I'm going to register them when I turn the device on. Then you have a couple of options. I'm going to go for just-in-time provisioning, which is the simplest option because I only need one provisioning template, and that provisioning template tells IoT Core what to do when that device connects.
We are going to start with that uppermost red square there. That is just demonstrating that you can make use of Amazon certificate management if you don't have your own PKI, your own public key infrastructure. And from that, we are going to create the certificate, the intermediate certificate that we will do the signing with, the signing for the credentials that are going onto the device. So we've gone to that larger of the purple squares. We have our CA. I have to register that with AWS IoT Core. That is how IoT Core is going to recognize our device. Remember, our device is not registered in IoT Core yet. From here, we have two options of how we are going to get these certificates and keys onto the actual physical devices. We can either go that horizontal path, and there we are going to kind of sign the certificates as they are at manufacture time, or we can do all the signing. An administrator can do all the signing and then hand all the certificates off to the manufacturing plant. If you do that, then we suggest that you use something like a hardware security module that will make sure that during transit you can track those, no one else can access them, and during the secure manufacturing process, that nothing in the manufacturing facility can access those keys. Okay, so now we are at the device manufacturer, the upper left little green icon there with a factory in it. And the factory is going to burn those credentials into the devices themselves. So now we're on the bottom left. Now we have the certificates and keys and everything in the devices. We're not yet registered with AWS IoT. So what happens? The device is manufactured, it goes out into the field, and at some point it gets turned on. When it gets turned on, it tries to connect. Now, it's going to get disconnected because IoT Core doesn't recognize it yet. So that process means that the device will connect and disconnect, but because it recognizes the CA that we registered, and it's going to trigger this kind of background, this back-end piece of code which is going to register our device for us in compliance, in according to how we've described it in our provisioning template. So when we set up the provisioning template, we would have said, which groups should it be in, what are its attributes, and all things like that. So that's all then happening in the background. Meanwhile, our device is disconnected. A couple of seconds later, it can try reconnecting. If that kind of back-end process is finished, it will then be successful. If it's not, it can just try again in a couple of seconds' time. And then, hey presto, we have all our millions and millions of devices provisioned and registered with AWS. Okay, great. So what have we seen? We have seen that AWS provide device-side software for exactly the same reason that these cloud services are provided as well. The services that provide that undifferentiating, just the stuff which it needs to be there before you can actually add value to your product. We've also seen how Amazon's stewardship of FreeRTOS has benefits which go beyond just the additional resources and the additional code that we are able to provide. This includes things like long-term support, of course, and the confidence that we get from these memory safety proofs. We've also seen that we don't stop just at the development, but also assisting people to really go to market at scale. So I hope that I have encouraged you to come and look at what we are doing. You can go to the freertos.org site. There is a forum where you can actually log in with your GitHub account. So that's your way of asking questions and actually getting replies, not just from the community, but also from the developers and maintainers of FreeRTOS. Come along to the Git repositories. I hope you get involved. Great. So again, thank you for joining us. And as always, we want to make sure that these talks are as useful to you as possible. This is a 300 level talk, so did we get the level right? Is there more information that you want? Is there information that you didn't require? All these things. Provide this feedback, please, and that just helps us improve year on year. Thank you very much.